Hi, my name is Kailash Raman, and today I'm going to tell you about the first of two companion papers on the semi-analytic inference of dwarf galaxy densities in the cold dark matter model. Part 1 makes a comparison of CDM predictions to ultrafaint dwarf kinematics. This work was done with my collaborators Benjamin Safdi, Dylan Folsom, Mariangela Lisanti, and Manoj Kaplinghat. Before we dive in, let's quickly remind ourselves what we learned from the dark matter density profiles of Milky Way satellites. These satellites are the smallest dark matter-dominated systems that we currently observe in the universe, and are therefore powerful probes of CDM and other dark matter models. As a canonical example, models such as self-interacting dark matter and fuzzy dark matter can modify density profiles relative to CDM expectations. Satellites are also often used in searches for dark matter annihilation, which is the topic of our second paper. In our work, we use a semi-analytic satellite galaxy generator, SatGen, to infer satellite dark matter densities, make CDM predictions, and compare to observed data. The main result of our work, highlighted here, is that we find that, at the population level, the most compact ultrafaint satellites are denser than expected in CDM, while the most diffuse ultrafaint satellites are less dense than expected. This discrepancy appears at roughly the 2.4 sigma level across all systematic variations to our modeling. So how does this procedure work? We start by generating a large sample of realistic Milky Way satellites with SatGen. What SatGen does is it first samples a merger history for a Milky Way mass host, yielding a set of dark matter halos with infall masses and redshifts. SatGen then assigns initial density profiles and other characteristics to each halo, following prescriptions for halo shapes, concentrations, and stellar masses calibrated to cosmological simulations. In our work, we make the assumption that all satellites initially have NFW profiles. Finally, SatGen follows the orbital evolution of each satellite as it falls into the host, including tidal stripping effects. The end result is a population of tidally truncated NFW halos that we can then use for inference. The next step is to assign density profiles to real dwarf galaxies by conditioning the simulated halo population on observed satellite characteristics. In our work, we consider two observables, the stellar mass m star and the mass contained within the half-light radius of the dwarf galaxy m half. The latter is driven by kinematics through its dependence on the observed line-of-sight velocity dispersion. Another way of looking at this procedure is that SatGen sets a cosmological prior for halo density profile parameters. Alright, let's look at some results. First, we compare the m-half inferred satellite densities to m-star based expectations with various stellar mass-halo mass relations. Broadly, the higher luminosity dwarf galaxies have well-constrained densities, driven by their larger stellar line-of-sight velocity statistics, and are generally consistent with the CDM expectation. Moving to lower luminosities, we see an increase in satellites at both high and low densities, albeit with larger uncertainties. These fluctuations in densities have a correlation with half-light radius. To quantify this behavior, we use SatGen to set a CDM expectation for the circular velocities of dwarf galaxies at their half-light radii. The prediction roughly follows the expected NFW power law scaling of r to the 0.5, with corrections from satellites of different stellar masses getting placed in halos with different dark matter masses. The data, however, prefers shallower power law that is in 2.4 sigma tension with the CDM prediction. In conclusion, we infer satellite dark matter densities through semi-analytic modeling and uncover a discrepancy between kinematic data and CDM predictions. However, it is possible that we may be looking at unaccounted for systematics in the kinematic data, such as binary contamination, for example. Thanks for your time, and I encourage you to see part 2 on dark matter annihilation.